If you thought the latest images from the James Webb Space Telescope were impressive, what you're about to see will completely change your perspective. A new space telescope has quietly started sending back images so detailed, so vast, and so revealing that scientists are openly admitting they were not prepared for what they're seeing. The Euclid Space Telescope has just released its first light images. They don't just show beautiful galaxies. They expose structures we barely understand, patterns shaped by invisible forces, and a universe that looks far more complex than expected. I'm going to walk you through what Euclid has captured, why astronomers are calling these images revolutionary, and why some of them are genuinely astonishing once you understand what you're looking at. Euclid is not a normal space telescope. It was never designed to focus on a single nebula or zoom in on one galaxy. Its mission is far more ambitious. Launched by the European Space Agency in July 2023 and positioned 1.5 million kilometers away at the Lagrange 2 point, Euclid was built to map the universe on a scale never attempted before. Its ultra-wide field of view allows it to capture enormous portions of the sky in a single observation while still maintaining high resolution. This means Euclid can see individual galaxies clearly while also revealing how millions of them connect into vast cosmic structures. What makes this significant is that Euclid is not just mapping visible matter. It is also mapping the influence of dark matter through gravitational lensing, using subtle distortions in galaxy shapes. In other words, Euclid is showing us the large-scale structure of the universe shaped by something we cannot see directly. When Euclid sent back its first mosaic of the southern sky, scientists were stunned by the scale. In a short observing window, the telescope captured 260 images covering an area of sky 500 times larger than the full moon. When stitched together, these images revealed millions of galaxies. This represents only a small fraction of the final map Euclid is expected to create. Researchers can now zoom from large cosmic structures down to individual galaxies without losing clarity, revealing how matter is organized across vast distances. This mosaic is a preview of one of the largest and most detailed maps of the universe ever created. One of the major discoveries comes from the Perseus cluster, located about 240 million light-years away. This region contains over 1,000 known galaxies and over 100,000 background galaxies. Closer inspection revealed more than 600 previously unknown dwarf galaxies hidden within the cluster. These faint objects had escaped detection until now. Dwarf galaxies are important because they are highly sensitive to dark matter. Their shapes and distribution help trace where dark matter is concentrated. The discovery suggests dark matter structures may be far more complex than previously thought. Euclid's images also reveal new details in nearby galaxies, star clusters, and nebulae. It has identified faint stellar populations, low metallicity stars that resemble early universe conditions, and possible free-floating planets not bound to stars. These findings suggest the universe is dynamic and constantly shaped by visible and invisible forces. Across large scales, galaxies are not randomly distributed. They form vast filaments stretching across hundreds of millions of light-years, connecting at dense clusters. This structure forms what is often called the cosmic web. Galaxies follow these invisible pathways shaped primarily by dark matter. The universe appears to be structured like a vast network, where matter flows along these filaments and collects at intersections. Another major capability is measuring gravitational lensing with extreme precision. By detecting small distortions in distant galaxies, Euclid maps where dark matter is located. These distortions reveal massive invisible structures that bend space and influence everything around them. Dark matter does not emit or reflect light, yet it outweighs visible matter in the universe. Euclid also observes galaxies so distant that their light began traveling more than 10 billion years ago. This allows scientists to study the universe's history across time. Early results suggest galaxies formed and clustered faster than expected, and that cosmic structure developed earlier than current models predict. This raises new questions about how gravity and cosmic evolution work on large scales. Another important aspect is cosmic voids, enormous empty regions between galaxy clusters. These voids are shaped by surrounding matter and may be influenced by dark energy, the force driving the expansion of the universe. If confirmed, this would significantly alter our understanding of the universe. As data grows, scientists are facing a major challenge. The sheer volume of information is enormous, involving billions of galaxies. Understanding it requires advanced computational systems and machine learning. In many ways, interpreting this data depends on tools that go beyond direct human analysis. Euclid is also revealing gaps in our knowledge. Many familiar regions of space contain hidden structures that were previously undetected. This shows that even well-studied areas of the sky still hold surprises. By combining distance measurements and imaging, Euclid reconstructs how the universe evolved from a nearly uniform early state into the complex structure seen today. Evidence suggests this process may have occurred more rapidly than expected. With only a small fraction of its mission completed, Euclid is already reshaping cosmology. The majority of its survey is still ahead, and future data may lead to further revisions in our understanding of dark matter, dark energy, and gravity. The key takeaway from these observations is that most of the universe is invisible. What we see, stars and galaxies, is only a small part of a much larger structure governed by unseen forces. Galaxies form within dark matter halos, and large-scale cosmic structure determines where they exist and how they evolve. Even empty space is shaped by these forces, stretching and expanding under their influence. Ultimately, Euclid is revealing a universe that is highly structured, interconnected, and far more complex than previously understood. And this is only the beginning of what its full survey will uncover. As Euclid continues its mission, the most important discoveries are no longer just coming from images, but from patterns hidden inside the data itself. Scientists are now using advanced algorithms to analyze the millions of galaxies already mapped. What they are finding is not just structure, but repetition, cosmic patterns that appear across different regions of the universe in ways that were not expected. Some of these patterns suggest that galaxy formation is influenced by deeper rules embedded in the fabric of space itself. It is no longer just gravity shaping the universe, but a combination of gravity, dark matter, and possibly unknown physics working together. One of the most surprising developments is how consistent the cosmic web appears across different time periods. Whether looking billions of years into the past or closer to the present universe, the same filament-like structures keep appearing. This raises a serious question. Did the universe organize itself early and then simply expand, or is structure continuously being rebuilt as it evolves? Euclid is also beginning to detect subtle irregularities in the expansion of space. These are extremely small deviations, but when measured across billions of galaxies, they become significant. If confirmed, they could suggest that the expansion rate of the universe is not uniform everywhere. Another major focus is dark matter distribution. Early maps show that dark matter is not spread smoothly. Instead, it forms dense clusters connected by thin bridges, almost like a web of invisible matter holding everything together. Galaxies are simply forming along these bridges, like lights turning on along hidden cables. Even more intriguing is the possibility that some regions contain far more dark matter than current models predict. These overdense areas could be influencing galaxy motion in ways we do not yet fully understand.